Hey, seventh graders, it's Mrs. Johnson, and I am going to walk you through your notes for the periodic table. Okay, so the first thing you'll want to do is make a copy of the notes with this link right here. When you make that copy of your notes, you should put that in the new folder you created yesterday. It's in your Science 7 folder, and it's labeled Unit 3. After you do that, what you're going to do is you're going to write for 2 minutes everything that you already know about elements and everything you already know about the periodic table. You're going to write that in this box right here. It's okay if you don't know a lot about the periodic table, but anything that you can think of that maybe you've seen or heard before. So pause the video and write for 2 minutes. All right, welcome back. You happen to have your very own periodic table in the back of your textbook. It's actually in all of the textbooks, but you should have received this either today or tomorrow in class, so maybe you haven't gotten it yet, but you will get it if you haven't gotten it yet. Or you should have picked it up last Friday if you're a distance learner. Okay, and in the back section of that, the reference section, there's a picture of the periodic table on pages R12 and R13, and then R14 and 15 have some more information that you might want to use as a reference. So we will periodically reference this periodic table. So a little bit about the periodic table. It was put together by a Russian scientist named Dmitry Mendeleev, and he's the one that kind of put the puzzle of the periodic table together. So let's watch this video to see how he did that.
Our Earth is a collection of puzzle pieces that make up the universe. In the vast darkness of space, the universe is lit by stars, which could one day become a supernova and create all of the puzzle pieces that we know today as the elements. All elements were formed and released into space by exploding stars. For centuries, humans have tried to discover what makes up the world around them. Little did they know that all the pieces they needed were right under their noses. The discovery of these pieces revolutionized our understanding of the world and allowed for the creation of what might be the greatest gift to science, the periodic table. So, where are these elements, and how do we find a means to order them? Well, believe it or not, ancient civilizations were very much aware of many elements around them, but they did not identify them as the pieces of our universe. Elements like gold, silver, and copper were easily spotted by ancient cultures and were used for multiple purposes like jewelry and tools. Why were these elements spotted so easily? Think of the periodic table as a puzzle. The corner pieces or edges of a puzzle are generally the easiest to find and place because they stand out with their smooth edges and clearly don't interlock with other puzzle pieces. Like puzzle pieces, elements can be choosy on who they interact with. Some like to interact with other elements, while others do not. The elements that do not interact with other elements are easy to pinpoint, while the ones that like to interact with others are difficult to find. Gold, silver, and copper are some of the choosier elements, so we can find them easier. So let's fast forward to the late 1600s, where Hennig Brand, a German alchemist, was busy working in his laboratory. Like many other alchemists of his time, Brand was trying to extract gold from the human body. Brand hit upon what he thought was the most obvious answer to his problem: urine. Urine is golden coloration and could perhaps have gold in it. So Brand collected as much urine as he possibly could, much of it being his own. Then he decided to boil it down in hopes of obtaining gold. So Brand boiled his, urine down until he collected a paste and heated the paste to a very high temperature. Eventually, smoke appeared and the material burned brightly and violently. Brand had unknowingly isolated phosphorus from his urine. This was the first time anyone had discovered an element, but he didn't really understand what he had done. At the time of Brand, the concept of an element had not been discovered. Instead, ancient Greek principles of objects being composed of earth, water, air, and fire were predominant. It wasn't until the work of Antoine Lavoisier, who is now known as the father of chemistry, that science defined what an element was. Lavoisier defined an element as a substance that could not be broken down by existing chemical means. Lavoisier created a list of the known elements of his time and tried to put the elements in some sort of order in which they could be classified, such as gases or metals. He was the first one to try to put the puzzle together. This was just the beginning of a means to organize the known elements of his time. Many other chemists then came along to make the puzzle clearer. One of them, John Dalton, weighed the elements and arranged the puzzle by weight. German chemist Wolfgang Dobereiner later combined elements to see how they reacted with one another. What he found was that certain elements shared similar properties and reactions. For example, when pure lithium, sodium, and potassium are exposed to water, they will react violently and skid across the surface of the water with sparks. The scientists then realized that these similarities are no coincidence. Elements belong to families that share similar properties. But the chemist who finally put the puzzle together was Dmitry Mendeleev. He created cards of each known element and tried to order them based on atomic weight and their known properties. The story is that he stayed up 3 days and 3 nights. He finally fell into a deep sleep and he dreamed about a table to order the elements. Mendeleev was not only able to create the periodic table, but he was able to predict elements that were not yet discovered. The puzzle of the periodic table of the elements was solved.
All right, so what are we going to be doing with the periodic table? So what the periodic table does is it shows all known elements in the universe, and it organizes the elements by their chemical properties. Okay, so if you look at the periodic table here, we can see a couple different patterns, okay, and these colors are showing some of the different patterns that we see. Okay, we also can see if they're solid, liquid, or gas, and that would be at room temperature based on their font, I guess. So the gases are white with like a white or black outline on the white. The liquids at room temperature are blue, and the solids are black. Okay. So updating your notes. If we want to read a periodic element square, okay, we'll see some specific things, and these are going to be updated in your notes. You can kind of see what it looks like, okay, but we're going to fill in this bottom part down here too, okay. So the atomic number, this atomic number actually correlates to the number of protons that that particular element has, okay, and the number of protons is what defines an element, okay. So if you add protons, it's going to turn into it would be a different element then, okay. Oops. Sliding around here. The symbol is the letter, the representation. Then we have the name. And then this down here is the atomic weight. So the atomic number, as I said earlier, is the number of protons found in the nucleus of an atom, or the number of electrons surrounding the nucleus of an atom. So most times, if we have a non-charged atom, the number of protons and electrons are going to be the same. The symbol is an abbreviation of the element name, and it uses, a lot of them use Latin, and so sometimes it doesn't really go with the name that we call it. For carbon, that makes sense. It's a C for carbon, but that doesn't follow that pattern for everything, and you'll see in a minute. Atomic mass is the number of protons and neutrons in the nucleus of an atom. Now, because neutrons are neutral, there doesn't have to be a specific number of them in a particular element. Okay, so where there's always going to be 6 protons in carbon and usually 6 electrons, there doesn't necessarily have to be 6 neutrons. Typically, in carbon, there is 6 neutrons, because 6 and 6 add up to 12. Okay, so if we want to know the number of protons, electrons, and neutrons in an element using the periodic table, okay, the number of protons is going to be equal to the atomic number. Okay, the number of electrons is usually going to be equal to the atomic number. For our sake, we're going to say that that's true. If we have something called an ion, then that might not be true. And the number of neutrons is going to be the atomic mass minus the atomic number. So here we would have 12.01 minus 6, which is actually 6.01, but we would include that as 6. Okay, so that's what you are putting in your notes. You're filling out the bottom of this, and then save these notes for later on.